When I think back about my student experience and also my work experience when I'm analyzing power generation equipment, power plants, I've got to tell you that my memory is that the hardest component that I remember analyzing is the feedwater pump. Now, there's some reasons for that, and I don't know why. I can tell you I found it to be the hardest, but I thought I'd pass that along to you. So if you find that you're struggling with feedwater pump calculations, just recognize that you're not alone. Okay, so this section is feedwater pump basics. Part of this is going to be a recap or review of what, quote unquote, you already know. Now, I have to tell you that I had to practice at these fundamentals that I already knew to really get good at them. And so again, if you find that some of this stuff is hazy to you, or you definitely need some review, again, you're not alone in that dilemma. So let's see. Here's our Rankine cycle with our four basic components, and of course, this video is going to be all about how do you do an analysis of the feedwater pump, states 3 to 4. And let's see, where are we on our TS diagram? Well, here we are over here. We're coming in as saturated liquid into the inlet of the pump, saturated liquid. We're increasing the pressure from P2 up to P1, or in other words, P3 up to P4. Either of those are perfectly good to say, okay? But our job for the feedwater pump is to go from saturated liquid up into the compressed liquid zone, compressed liquid phase. That's an important thing to remember in your mind. Now, the recap is how did you draw your sketch in the first place? I tried to communicate to folks that here's a basic process centrifugal pump with one single stage, but then recognize in most feedwater pump applications, you're having to pump increase the pressure up so high to get into the boiler that you're going to need multiple rotor or impeller stages to increase the pressure to that level. And so these are some pretty good photographs of, let's see, 1, 2, 3, 4, 5 stages of feedwater pump. And then here's the operational look of that, and I can sort of see these lumps here in the casing. That's be where the rotors or impellers are housed. I can see 1, 2, 3, 4, 5 stages there. And here's an example of a electric motor-driven feedwater pump. Sometimes in the world, these feedwater pumps are driven by steam turbines, especially since there's an ample supply of steam available. And so that could be a reason to have a steam turbine-driven feedwater pump. Let's see, a couple of videos to recap. Let me move my picture here. You say, well, we've already covered a lot of this. I totally agree. All the way back in Chapter 4, Open Systems, we introduced some fundamentals about pumps using the first law to analyze a pump. And then we got even a little more sophisticated and we defined pump efficiency in Chapter 6. And so if you might want to scratch down on a piece of paper, it might be worth your while to go look at Chapter 4, Part 9, which are pump fundamentals, and Chapter 6, Part 14, where we define formally what is pump efficiency. Okay, well, here, what's your sketch going to look like? I hope your sketch you're pretty familiar with. Okay, I've drawn this pump sketch enough times to see what it should look like. It should not look like a cloud or a box. It should definitely look kind of like a centrifugal pump. So here we are. We're coming into the inlet eye of the impeller at state 3. It's going to be saturated liquid. Coming out, it's going to be compressed liquid. I'm showing W dot out, of course, like I always do, but I am very clearly showing it's less than 0. W dot out for the pump is a negative number because it takes power to drive the pump. An important green text box here, it says substance. incompressible liquid water. That is a key thing to remember. And I think that's one reason why I kept getting caught up short in my pump analysis, that somehow that slipped my mind as a student. All right. So it's a good reminder. What do we have? We have an open system, steady state, steady flow, one inlet, one outlet. So therefore, m dot 3 equals m dot 4. We're just going to call that m dot. Okay. And another thing is, I'm not showing heat added to the casing of this pump. That's because we're going to model the pump as fully insulated. No heat transfer between the pump casing and the surroundings. And we're also going to say for this analysis that changes in kinetic energy of the feed water are zero, as well as changes in potential energy, zero. All right, so that's where we're starting from. That's our model, that's our sketch. Another recap that I really need to mention here, rather than just glossing over it, is look at this equation 6.51b. It's not necessary that you have this in your head. Don't be, oh gosh, I should have remembered that. No. But this is an expression. What is this equation 6 from chapter 6? It's a statement of for any open system undergoing a reversible process, W dot over M dot, that would be little w, is minus the integral of VdP. Wow, that's different than a piston and cylinder, isn't it? That's different than a closed system. And that was one thing that I had a rough time capturing as a student, is for a closed system, work is an integral, but I'm not going to say what it is. You know what it is. And for an open system undergoing reversible process, one inlet, one outlet, minus the integral of VdP. And so this is important, and I've blown up this equation into a much larger font so you can see it with your eyes. W dot over M dot for a reversible process is minus the integral of VdP. Now, for a compressed liquid, do you see how we're going to simplify this fundamental? How we're going to simplify this fundamental if we have an incompressible fluid? V is constant, and we're going to simplify. Okay, and so another recap, all the way back to chapter 3 about incompressible liquids. And so I have kind of repeated out of your textbook, section 3.10.1, where it says, look, if you need the specific volume of a compressed liquid, okay, an incompressible fluid, all you have to do is go and look up V sub F, the specific volume of saturated liquid at the temperature, not the pressure, at the temperature of the fluid. Okay, and so this is very important, and also a place that I made some mistakes as an undergraduate. If I'm looking for V3, if I'm looking for little V3, I've got to remember to go to the temperature table. I've got to know what is T3 and look up the specific volume at T3, not at P3. Okay, so it's going to, in other words, it's a saturated liquid. Okay, there we go. There's another good recap. All right, now let's see. So there we go, and you get the idea of, I'm going to try to work you through how will you analyze the pump? How will you analyze the pump? What are you looking for? Well, we're going to be looking for the actual power required to drive the pump, as long as you know what the pump efficiency is, okay? And you're also going to need to perform a first law analysis on the pump, because you're going to need H4. You're going to need H4 to put into your first law analysis for the steam generator. You've got to find out what's the value for H4. I'm going to try to help you work through this. Step 1, determine V3 and H3. Okay, so if you know the temperature, you must know the temperature of state 3, or if you know the pressure of state 3 and its saturated liquid, pressure and saturated liquid, you can look up, you're going to look up and write down V3 and H3, which is going to be V sub F and H sub F at whatever the temperature is. Okay, hope that helps. So that's a key. That's a key point to make. Step 1, determine V3 and write down H3 as well. You're going to need it. Okay, step 2, determine the reversible work for the pump. In other words, if the pump were reversible, and also our model is adiabatic, we can apply, if it's reversible, we can apply this fundamental. W reversible is minus the integral of V dP. And we remember, I can pull V out of the integral because it's incompressible. V is constant. And so here you see we've got W reversible is minus V, which would be V3 times P4 minus P3. Well, let's see. There's a pesky minus on there, isn't it? So W reversible for the pump is V at the inlet. That would be like V3 times P3 minus P4. Okay, that's not a formula. That is derived from the fundamental statement. Now, recognize P3 is a lower number than P4. That makes sense. So work reversible for the pump is going to be a number that's less than 0. Little w less than 0. Makes total sense. Okay, so V3. Oh yes, for this step 2. In SI units, you're going to have V3 in cubic meters per kilogram, and your delta P, P3 minus P4, is going to be in kPa. And if you work through the units of that, you will see that the resulting units are kilojoules per kilogram. Easy. English pump, let's say English system. V3 is going to be in cubic feet per pound, and delta P has got to be in pounds force per square foot. Notice I've bolded that, right? Not pounds per square inch. Delta P's got to be in pounds force per square foot. And what's that going to give you? We can visually do the multiplication here to see that's going to give us foot-pounds force per pound mass. Yikes. That's not what we need, because ultimately we're using the first law and we need to be in BTUs per pound. So once you get your value of W reversible in foot-pounds force per pound mass, you've got to use this conversion. 778 foot-pounds force equals 1 BTU. And you'll apply that conversion to get reversible work in BTUs per pound mass. Little w, W dot over M dot, BTUs per pound. That's important. Okay, step 3. You just found W reversible of the pump. And nearly always you have or you can find the pump efficiency, eta pump. So all you do is you solve for W actual. It's going to be W actual is going to be, this is a typo. This is a typo, isn't it? So please make a note. W actual is equal to W reversible of the pump divided by eta of the pump. Look at that. So you're going to have to forgive me, right? So this is incorrect. Incorrect. W actual is equal to W reversible of the pump divided by the pump efficiency. Ah, what a blunder. Sorry. Okay, so let's say, so even after catching my blunder, you've caught my blunder. You say, okay, I got it. I've got that straightened out now. I've solved for W actual. Recognize that W dot actual over M dot is little w. And so if you're asked to find the power required by the pump, you simply multiply little w actual by M dot. Okay, so that's step 4. Wow, how embarrassing that I didn't check my work in that previous slide. Okay, now I told you, looking ahead, we're going to have to analyze the boiler, so we need H4. We need H4 actual, because we've got an actual pump, right? And so how will we do that? We'll apply the first law. If you don't know what to do, apply the first law. See if that can help you. And it can in this case, right? So Qn, that's 0, right? So we've got an insulated pump minus W actual. Just found it, okay? Equals what? No change in kinetic, no change in potential energy. So we've got equals H leaving minus H entering. H3 we've already looked up. And so it's sort of child's play to get H4 actual is H3 minus W actual. Wow, let's see. Wow. Well, that's going to be, if W actual is a negative number, H4 actual is going to be bigger than H3. And that's exactly right. You're putting energy into the fluid. You're going to cover this in your fluid mechanics class. Putting energy into the fluid, you're bumping up the enthalpy of the compressed liquid leaving the pump. Okay, so I threw a lot of steps at you. I had one big blunder in there, but thank goodness I caught it at least with my eyes. Shame on me for not proofreading more carefully. But if you want to go and see the nuts and bolts, the devil in the details, particularly of this pump computation, problem 816 I've done in English units. And so going to homework solutions playlist and problem 816 may help you see how to get through the computational details, of analyzing all the components. Okay, well, gosh, we have worked through all four components of the Rankine cycle. My slides have not been perfect, but you're sharp enough to see little little blunders I made, and you can correct for those. So I hope working through each individual component separately helps you see the big picture. You see how much we're using the first law. We're not just putting down a bunch of special formulas and plopping them down. Most of the time we're using the first law. A couple of times we're using the second law, and then we're just using plain old good common sense to determine the thermal efficiency of the plant. Okay, hope that helps, and I'll see what's coming up next.